Hello and welcome to our today's webinar about the topic we backup your application, a hot swappable backup solution. My name is Frank Puhane and I'm working for Würth Electronics in the capacitor and resistor division. And here I am the lead of the technical engineering and in charge of product services and application support. And formerly I designed power supplies and industrial controls and also wrote software for this kind of machinery. So today's agenda is as follows, as you see here. We will have a short roundup about supercapacitors, like their classification, their model parameters, and their charge and discharge behavior. After this, we will have a look into the application and how we design in especially the supercapacitors. So let us start first with the classification of the supercapacitor. Supercapacitor is the generic term of 3 different technologies, as you see here, the 3 different technologies. The most used one is electrochemical double layer capacitor, also known as EDLC, and then followed by a pseudo capacitor and at least the hybrid capacitor. The difference of these technology makes the design of the electrodes. So for supercapacitors at Würth Electronic, we use activated carbon as an electrode material. And when you change the design of the electrodes, we'll also get different capacitors like pseudo and hybrid capacitor. Yeah, so what makes the supercapacitor so super? When you're looking at the charging and discharging possibilities, this product is quite unique. You can charge and discharge the supercapacitor very fast, and they have also a long cycle life of around 500,000 cycles for charge and discharge. In addition, also the power output is around 10 times higher than a lithium-ion battery. But of course, every technology has some limitations. And for the supercapacitor, it is the low energy capacity. It's around 30 times lower than lithium-ion battery, and they have a linear voltage dependency. When you draw energy out of a supercapacitor, the voltage falls linearly. But I show you this also later. Also compared to traditional capacitors, it's quite the same. But of course, the power output compared to a normal capacitor is much bigger. But also, comparing the rated voltage of traditional capacitors, they are higher. And again, batteries, they have higher energy density and of course also a constant voltage. But have a low power output and a relatively low cycle life. When you imagine the phone accumulator, they have limited charge cycles. And what you have to keep in mind when you try to charge the lithium-ion battery too fast, you may need also an extinguisher because they can also burn when you don't have an BMS system. But let's go back to the supercapacitors, especially looking try to answer some questions like the electrodes, how it looks from EDLC, how we can get these large effective area, and also what is the Helmholtz layer. Starting with the Helmholtz layer, it is an electrostatic storage of the electrical energy by separation of charge at the anode. And the double layer refers to 2 parallel layers of charge surrounding one object. You see it on this kind of picture. You see this with a charge and the surrounding charge, and therefore every charge on one side of the electrode is balanced by a mirror charge on the other side. And when you want to know how the supercapacitor looks in reality inside, it's here in the middle, and those 2 pictures. It looks quite the same like a normal traditional electrolytic capacitors. It's also wound type. You have your contact pins. It's stitched to the foil and so on. But of course, the inner structure is different. So the design of the inner structure is quite unique. Yeah, so there are some parameter. Yeah, it's important to know when you want to use it in your application. And for supercapacitor, the main parameter is the charging and discharging time, as well as the power and energy capacity. So the rated voltage defines the output power and the energy storage capacity. And this rated voltage is limited for the EDLCs by electrochemistry, and it's the so-called decomposition voltage. And for non-aqueous electrolyte, what we are using, this is around, or this between 2 volt up to 3 volt. And yeah, it depends what kind of electrolyte it's used, the rated voltage change. The capacitance defines the energy storage, of course, and the ESR defines the maximum power output. And the isolation resistance defined the charge storing capabilities. And in the right side, the performance parameter, you see everything combined. So depending what kind of specification we have, the energy storage, the power output, and also the RC time is changed. Yeah, if we are now going to compare the charge and discharge behavior of the EDLC with behavior of a battery in general, so the charge and discharge current of an EDLC are higher than for batteries. So the charge current and discharge current here compared to one with the battery. The voltage drop is at a constant current linear with the time because we have still a capacitance, and that means I can charge and discharge EDLC very fast, but I have a voltage drop due to the ESR when I start to discharge, and the voltage drops falls further linear. So this is what you see here. So this little drop here when you want to start to discharge comes from the ESR, and due to leakage current, it's also the voltage falls when there's no providing no energy. And batteries, they have almost a constant cell voltage and at a constant current operation. So when there's no charge anymore, it's quite stable. And when you start to discharge, it's also quite the same level. But you cannot charge and discharge it so fast compared to supercapacitors. Yeah, this was the short roundup about the supercapacitor technology itself, and now we will have dive into the application we built up, so the solution what we built up. Yeah, as you see, we use an analog device IC for the voltage regulation in our demonstration. The advantage is that the IC has some very nice features like hot swappable and also high power capabilities. We defined our application for that we want 30 watts for 15 seconds. So at the output in a backup case, we have 12 volt and 2.5 amp at the output. We have also further advantages like high efficiency, synchronous step down, constant current, constant voltage charging, and we can place 1 up to 4 supercapacitors in series. Also, when we have then the backup mode, it's a step up converter, and also the IC has some interface like an I2C or the SM bus, and you can transport data to the via I2C to a display, for example, to an Arduino, and manage the data you get from the IC. So one short differentiation between the hot swap and the hot plug, they are used normally in a similar way very often. This feature is necessary so that the right pictures you are seeing here that they are not happening. However, hot swapping is the replacing or adding components, so no shutdown or stopping of the running system occurs. And this is also done by pre-charging through a special pin, for example, when there's some connector or some soft start peripheral. When you now do the differentiation between hot plug, is an describes only the addition of a component that would expand the system and have no significant interrupt to the system itself. So there's a little bit different, but also in the data sheet from the IC, they use it in a similar way. So what we have in our system, this is the specification of a demonstration. So we have 24 volt the input and the output rail. So in normal operation, we have the same output voltage like the input side. And the voltage in step up mode, so in failure mode, is 12 volt for industrial supply controls, and the voltage of the supercapacitor bank is 10.6 volt. So yeah, the supercapacitor bank 10.6 volt. Of course, we could go higher for the bank voltage to have more energy in the system, but we go for some safety margin. So the single cell voltage of the supercapacitor is 2.65, so we have a little bit safety margin. The 10.6 volt leads that there is no direct supply from the supercapacitor bank because it's a lower voltage than the output voltage in backup mode. So here we supply over the step-up converter here. Switching frequency is 450 kilohertz, and the input current is limited to 2.5 amp. Also, we have a constant power discharge, and we supply the load and charge the supercapacitor at the same time. Yeah, to show that we are operating in a high efficiency region, I placed here the diagrams from the IC manufacturer datasheet. The left one shows the efficiency in boost mode. We have 12 volt as the output voltage and around 2.5 amp current. Also, the charger efficiency itself in the right picture is quite high, so we have a high efficiency system. Yeah, so now let's dive a little bit deeper in how this thing is working, how the demonstrator is working. So the example begins here. So with this hot plug event, when the input voltage and the capacitor bank voltage is 0. And then we plug it into an power supply suddenly and at a point labeled at hot plug. And there's a very small inrush current here into the drain capacitance of the hot swap FET connected to the input. This is this small spike in the waveform. And depending on the rise rate of the input voltage, this is the way the duration amplitude is changing. And then we have some debouncing. So the IC qualifies the input as good using the under voltage lockout and over voltage lockout comparators. And when the input time, when this timer expires and everything is good, it starts working. Then it turns on the hot swap FET. So this is here debounce inverse current control. Turning on the hot swap to charge the capacitance on the output. So no capacitor, not the supercapacitor bank, but it charged the output capacitor from the V out in a controlled way. And during which time both the input current and the rise rate of the output are controlled. And this is really important because this results in a really low constant input current, and the rise rate of the output is controlled until the capacitance at the output is charged. And when the voltage at the output is stable, the charger is allowed to start charging the supercapacitors. So first in constant current mode here. So here's the constant current charging. You see here the voltage at the capacitor rising. Here's the input current. So it's quite high as defined. Then you do it in constant current mode. Then in a constant power mode. So it's here when there's some bump here, it's constant power. And then at the end in a constant voltage mode. And the IC is doing some balancing. So it's yeah. Also, when supercapacitor bank is fully charged, you also some balancing. And the IC keeps the capacitor charged and balanced and ready for backup. So while fully charged, the IC can also measure the ESR and the capacitance. So now let's start talking about the passive components, how you can choose the supercapacitors for such kind of application. A good tool for that is our support node SN009. Here we describe a few steps what is important to consider. And first, we had to define the mode of discharge. With our IC here, it's constant power. And after that, we calculate the needed capacitance. We want to supply an application for around 50 seconds with 30 watt. So we calculate here the needed capacitance. So we need 450 joule. And with the parameter of the supercapacitor bank and the cutoff voltage of the IC, we calculated the capacitance. So we assume the cutoff voltage of the regulator with 2 volt. And then we get our 4.2 farad. The charging is done by the analog IC in the 3 phases: constant current, constant power, constant voltage. So it's optimal condition. And the highest possible charging current is around 6.4 amp. So this is no problem for our supercapacitors because you can charge it with higher currents. The supercapacitors are all measured and stored in our online tool with Expert. So we have the impedance, the ESR, and the maintain voltage diagrams. They can be looked up here. And to determine the ESR, we charge the supercapacitor to defined voltage, for example, and then obtain the ESR when discharging through the delta of the voltage and the current. And one thing what is really nice to know is this maintain voltage. So we measure the resulting voltage of the supercapacitors after 100 hours with no charge anymore. So we charge it here. There are 3 lines. We charge it 8 hours, 24, and 72 hours. And you see when you charge supercapacitor longer, then it can hold up longer the voltage. So 72 hours is around 2.5 volt, 2.55. When you just charge 8 hours, after 100 hours, it's 2.3 volt. So it's really depending how long you charge the supercapacitors. Yeah, having a closer look to the supercapacitor bank, we put 4 supercapacitors in series connection, and we have a working voltage of around 10.6 volt in total. It results to a capacitance of 12.5 farad and a total energy of around 702 or around 700 joule. And the maximum output power would be around 3 kV with an ESR for one supercapacitor with 2.2 milliohm. On the bank, there is no onboard balancing because the IC from analog have some integrated stacked balancer. And what you see here with this circuitry here with the plug is just for that I can discharge the bank manually when there's some issue or when I want to send it somewhere. Yeah, what we see in the layout is also this pin header here. This is just because of some engineering play around with Arduino and some status bar we designed to show the energy what is left in the supercapacitor bank. Yeah, balancing is really important because of the tolerance of the products. This example here shows when you have 2 parts connected in series, total capacitance here would be 10 farad. The tolerance is +10 and -30%. They charge to 5.4 volt. And here the worst case scenario would be that I have 9 farad and the other one has 13 farad. And when we now calculate the voltage across the capacitors, we get for the C1 2.21 volt and for C2 3.19 volt. And of course, yeah, the supercapacitor have some safety margin, but the 3.2 volt is much too high for 2.7 volt rated supercapacitor. So this is why we have to balance that there's no over voltage to one part. Yeah, to prevent this, it's necessary to balance the charge for the supercapacitors. There are two possibilities to set up balancing. You can do it passive or active. Passive you can use if operated primarily under DC conditions. It's quite low cost and it's also really slow. Also, it has high losses. Active balancing is often or is used when you have charge and discharge cycles very often. Yeah, it's high cost compared to a resistor when you want to use for passive balancing, but it's also quite fast and you have no loss. So imagine you place an quite low passive resistor that you want to have and fast balancing. Then yeah, you have also a high leakage current, for example. Yeah, what we show here, yeah, because supercapacitors, they are lose capacitance as they age, and also in addition, the ESR will go up due to the aging. We have a very good overview about this topic as we created and defined our tools for the calculation of the lifetime of our supercapacitors. This is shown in the two diagrams here. The left one, what you see here, shows the remaining capacitance after 10 years, depending on which operating temperature the supercapacitor is used. And the right diagram shows the same information, but in a more sophisticated way, because we also take into account the applied voltage. And the loss of capacity, the aging, can also be compensated by the IC a little bit, what we are using. It's you can change the supercapacitor bank voltage with the IC, and there you can increase it, and you get more resulting lifetime. But one interesting information here, when you look at a remaining capacitance, when you use it at 65 degree after 10 years, you have more or less no capacitance left. And with the right diagram here, so this is this bar is the remaining capacitance, and here is the voltage, here's the temperature, and then you see quite good when you reduce the single cell voltage and reduce temperature, you gain your lifetime, also you gain your capacitance and a low ESR. So this is really important. Yeah, to show the lifetime or what it means, we created some use case. For our example, we said we have 10 hours at 40 degrees and 2.65 volt, 2 hours at 40 degrees and 1 volt, and the other 12 hours are no operation. We have the bank voltage of the 10.6 volt. This leads to the single cell voltage of 2.65 volt. Temperature profile is a maximum 40 degrees. And we calculated before a few slides before the needed capacitance with the 4.2 farad. And we have a total capacitance in the supercapacitor bank with 12.5 farad. Also, when taking account the tolerance is minus 10%, it leads to a value of 11.25. And so it's still a lot of safety margin. But now it's when we are looking after 12 years, we have still a capacitance of around 5.6 farad. So still enough. We lose 50% of our capacitance, but still enough to have our operation still running. So with this diagram here, this is our mission profile here, and this is the remaining capacitance. And you see after my 12 years, I lose 50% of capacitance. and as I said, still enough to supply our application. And lifetime depends on voltage and temperature, and the current is increasing the self-heating, so self-heating leads to temperature. So this is included in the temperature when we look at the lifetime. So, but now what happens if we change the voltage of the supercapacitor bank and also the voltage of the single cell? And we calculated two situations. One is with a lower cell voltage and one is with a higher temperature. Reducing the cell voltage leads to an increase of our lifetime. So in the left diagram here, we see that the remaining capacitance after 12 years is now still 70% of the initial capacitance. But temperature, as you see also before, is a really critical point. In the right diagram, when we say operating temperature is 65 degrees, it leads to a capacitance drop to nearly 0 farad after 12 years. So here's 12 years. It's more or less, no capacitance anymore. So the charge and discharge current increase self-heating, and so the temperature of the component. So this is how we check the currents. Yeah, this is our demonstrator. This is how the demonstrator build up. And please see here the schematic. I know maybe it's not so good to see, but I want to show the complete schematic. So important for us from Wood Electronics is the input filter because of the noise from the input rail. So the left side, there's an input here. Also you place the filter. The output filter here. Because the IC works in boost mode when the supply voltage is down, we need some filter at the output side. Also, the output and input capacitors are important to have a good signal and low ripple voltage. This is here, input and output capacitor. And here on the right corner, our supercapacitor bank is connected via some terminal blocks. And the current sense resistor and the MOSFETs are taken with good care to achieve the high charge current and tight limits of the application. So this is how the final board looks like. We implemented also an additional status bar to monitor the charge of the bank in hardware. This is here. This is the EDLC stack voltage. And the CIF connector is used to send the data to an Arduino to display the data on a LCD. So here's the input. Then here's the filtering. These are the MOSFETs, the current sense, and here the output filter. This is the IC from analog. Here the MOSFETs for the step down, step up, input and output capacitor. Also the current sense for the switch, and here the supercapacitor bank is connected. Of course, we need also the supercapacitor bank to finalize our backup solution, and we connected the bank via some terminal blocks. In the charging phase, the IC supplies the output with a 24 volt and charge the supercapacitor. So this is in red. So this is I can supply the 24 volt to the application and also charge the supercapacitor backup or to charge the supercapacitor here. And in failure mode or in backup mode, the IC supplies the output with a 12 volt through the energy provided by the supercapacitor. So this is the yellow one. It goes here and then to the output, but then in 12 volt. I know to convince engineers that a demonstrator is really working, I captured here some oscilloscope picture. In the left side, you see the real charging curve in blue, and the red one is the output voltage. The scale on the right side is for the red curve. And please have a look at a light red marking here, what I show here. And maybe you remember that this is the picture from how the IC works at startup. And this is an ideal description. So the right side here, this is from the data sheet. And what you see on the blue curve and here in the red marked one region, you see there are slightly higher, so there's a small bump here. So that means that the charge current is slightly higher than shown in the data sheet. So this is also comparison between real operation and what is in the data sheet to show it's a real application. This is also the charging with load. So I supply the output 24 volt and charge the supercapacitor bank. Yeah, to show every behavior, please see here also the charging without load. Because I have no load, this is done quite fast, because also it depends what the source can provide. When you have a not so high power source, it takes longer to charge it, but as we had a quite good source here. And in the end, this slide shows the combination of the two charging situation, and what is here in the black marking here, or in the markers black and red, is the discharging time. And we see here that the discharging time is the 15 seconds, and this is for every it's every time the same. It doesn't matter if it's with charging with load or charging without load, the discharge is every time the same, and it works as we described. So we check it with an electronic load and also with a resistor network, and it works quite well for our demonstration. So in the end, let's have some design application review. What we have done or what we showed the last few minutes. We showed a backup solution with a size of 10 by 18.5 centimeter. It's around 4 inch by 7.3 inch. The input voltage is 24 volt, and the backup voltage is around 12 volt. And we can provide the output and power for 30 watts. So we have 12 volt and 2.5 amp. We used an eval board from Analog, and also used the software from this LTC 3351. We have we have a support node for the design in process. This is the SN009. We also have an application node in the pipeline to describe the whole process. And currently we are working on a supercapacitor bank calculation tool to have it in our online tool with Expert. And of course, we can support you in your design with calculating the lifetime, and also to help to select the bank when there's some when we know the specifications. That was it from my side about the demonstration description. And now I'm here to answer your question, but please give me a few minutes to check the questions, and then I will answer it. So one question was, could I explain the slides where we see the cell phone and charger burning? Of course, this was this slide. Oh, it was too fast from my side, sorry. So this one, this is a really, there are pictures to how to say, of course it will not happen. So this is to make it clear that you use this hot swap and also hot plug, that your system, that there is no failure in the system, that you don't have to shut down your system. And also, of course, when you plug in an application with a high energy density, that there is no spark and so on. This is why this IC makes this spike at the beginning to check, okay, is everything there? is the under voltage lockout, over voltage lockout correct? And this is why this feature is really important. When you compare it maybe to the wireless power, there's also some handshake to check if it's an G receiver, that there is no 4-eigen object inside the transmission and so on. So this is also the IC uses this hot swap or hot plug functionality to check if the system is ready to handle also this high current. So this is why it's a little bit provocation here with this picture, but it shows that you need this functionality to have a safe operation. The slide 20. So the y-axis on the left diagram, it's the remaining relative capacitance. So for example, when we say 40 degrees, after 10 years, you have 20% left of your initial capacitance. So when we have 10 farad at the beginning, you will have 2 farad at the end. So this is the diagram on the left side. And just here, this is just the bar to see how capacitance left. So it's the same, also relative capacitance in percentage. It's the same on the left side. Yeah, this is a good question. Is this kit available? I'm in contact with the IC manufacturer to bring this as a kit. So it's good to know that that you are interested in this solution, that I can push it more. But I have no time schedule when this will be ready. But of course, you will know it when we do some marketing with this kit. Next question is, what is the minimum voltage that a supercapacitor can discharge? Is it till 0 volt or is it till a minimum voltage? So the good thing is that there is no limitation compared to the battery. So you can discharge it until 0 volt. There's no critical voltage like with a lithium-ion battery. But please keep in mind that you need some infrastructure that you can use it until 0 volt. So you need a really good step-up or SEPI converter, which operates to really low cutoff voltage. When there's some, for example, 0.5 or 0.2 volt ICs, then you can use it nearly to 0 volt, but there will be some voltage left in the supercapacitor because you cannot use it until completely 0 volt, but of course they will discharge itself and then they are 0 volt. And the last question what I see is, are there any special supercapacitor categories for energy harvesting applications? If so, what are the differences and how would supercapacitors managed in intermittent charging that would be happening? So as I know, there is no special supercapacitor for energy harvesting, but for example, we have our cylindrical style. So the smallest one we have is 3 farad at the moment, and it's 20 millimeter high. So when you have an energy harvesting application, it might be too big in size, and yeah, maybe you know that these coin type cells, they are of course flattened and quite small, but yeah, they use a serial connection inside that you get these high voltages, and yeah, it depends what kind of energy you need. Yeah, and also the charging, when you have with energy harvesting, when there is some charge, then you can charge the supercapacitors and time by time. But you have also checked the leakage current, because when there's maybe one day some energy and then 1 month no energy, then the supercapacitor will be empty. So then maybe you need a combination between battery and supercapacitors. So supercapacitors for the short time energy to store it and then transfer it to the battery. And then you have a really reliable system that would can be charged and discharged quite fast. Yeah, then that's it. There was no further question. When you have questions in the end, or when there are some questions upcoming, please contact us, we or me, or contact me. I help when I can, and I wish you a nice day. Thanks for joining, and yeah, have a nice day. See you. Bye.